Since we talk about both technological networks and socioeconomic networks in this course, the two examples that we pick are also from these two different kinds of networks. The first one is our old friend, capacity allocation in a wireline network. And now we have seen, say back in lecture 14, that one way to model the allocation of a fixed capacity among users is to maximize U of X, which is decomposed into the summation of utility for each source rate indexed by I, subject to the constraint of the optimization that X must be some kind of feasible capacity allocation vector. Okay. And the variables are the X vector. For example, here's a specific topology. Okay. You got L plus 1 sessions, indexed from 1 up to, actually from 0, 1, 2, up to L. Okay. The zeroth flow is a long flow. Okay. And the topology is a simple one. It's just a linear tandem topology with L links. So the 0th session is a long session that traverses all the links, and therefore you think would take up more resources, and indeed that's the case. Whereas the other L sessions are short ones. In fact, so short each one only go through one link. So these are the other L sessions, X1 up to XL, receiving that much data rate. Okay, so these are short. This is long. So the question is, how do we allocate fixed capacity, okay, on these L links to these L plus 1 sessions such that we can maximize some notion of fairness and efficiency? And let's say for now that each link have a fixed capacity CL equals 1 unit, say 1 megabit per second for all the L's from 1 to up to L. Okay, that's the constraint. And therefore, each link is really shared by 2 sessions, shared by the XI session, okay, the ith session, plus the 0th one, the long one. And they have to add up to be less than or equal to 1 unit for all the i's, okay, from 1 up to L. That's the constraint. Except now we want to formulate and then solve a new optimization problem where the objective function is not just the original alpha fair utility, because we know alpha fair utility is actually a very extremal point of view. It puts an maximum possible emphasis on fairness as long as Pareto dominance is not rendered meaningless. Okay, so it's an extremal viewpoint. A more moderate viewpoint would say, let's look at the entire spectrum of possibility using our newly discovered function f sub beta lambda of x, which we know can be written as this function, small f sub beta, only the distribution part acting on x, and then the summation of the xi's raised to the power 1 over lambda. If we maximize now this more general function as the objective, okay, rather than setting lambda to be an extremal value, still, of course, subject to the constraint that all the link capacities must be satisfied with the variables that are the xi's, okay, they're L plus 1 sessions, and then L links. If that's the new optimization that we try to solve, let's see what would happen to it. Now, skipping the numerical solution detail, whether it's centralized or distributed, here is the kind of trade-off that we see. Now, on the x-axis, I am plotting this 1 over lambda. As 1 over lambda becomes bigger, lambda becomes smaller, and the focus, the emphasis on fairness component relative to the efficiency component, relatively speaking, that is, goes down. On the y-axis, I'm plotting a couple of different things. First, I'm plotting the fairness component, the f sub beta part, versus the efficiency component, the summation x part. And as you can see, confirming our intuition, as lambda becomes smaller, the relative component of the fairness notion goes down, and the relative contribution from the efficiency component to the objective goes up. Now, second, I'm plotting the actual rate allocation, the optimizer, beneath the optimal solution. By symmetry, I don't need to plot all L of these short sessions. Okay, they all get the same thing. So I will just plot one of them. And then I plot the long session. This is the long session, this is the short session. And as fairness, relative importance, relative efficiency goes down, you see that the short sessions get more and more rates, the long session gets less and less rates. Okay, because it becomes easier and easier to accommodate a smaller rate for the long session, as long as that helps with gain in efficiency for the overall network. Okay. So these confirm our intuition. And if you pick this lambda, okay, to be a specific value, like in alpha fairness, then you don't get the whole range of trade-off. You only get a specific point, like this point of trade-off. All right, so now we saw the generalization of our earlier discussion on rate control in a network. Let's look at another example, and this will be the last example, not just for this course, this lecture, but for the whole course as well. And that's on this very touchy subject of taxation. Okay, now, taxation is an interesting subject because it serves many different purposes. Okay. Including supporting the basic operation of the government, to redistributing wealth, to encouraging growth in economic production, to penalize certain behavior, and so on and so forth. Okay, so let's take a small slice of that debate here. If you're in the U.S. and you read, say, New York Times editorial, you often see this argument that says, gee, the rich people are not paying their fair share of taxes. Okay, if you look at them, say, you know, they get so much a big percentage of total income per year, and yet they're not paying enough tax. Okay, because even the post-tax income distribution is still not equal. All right, let's try to make them more equal, and therefore taxation should take one person's money, take away from her, and then give it to another person and make him better off. So that means we want to look at the fairness of the post-tax income distribution versus the fairness of the pre-tax income distribution. Let's say before taxation, the income distribution is a gigantic vector x, and the taxation is a vector c. And then, therefore, x minus c component-wise is the post-taxation income vector. So I would like to look at the fairness value of x minus c and x. Now, of course, this taxation itself is a function of the income distribution x. Okay, so c is not some arbitrary constant vector, is a function of x. And this function really is driven by the tax rates and tax policies in general. Okay. However, fairness is much more than just asking, is everybody's income now about the same? Fairness is also asking about, is somebody paying too much tax relative to the other people? In other words, are some people sharing an unfair burden of the tax? And if you read in the U.S. Wall Street Journal editorial, that's often the argument that says, look, almost half of the U.S. population pay no federal income tax at all. In fact, some of them get negative tax. They actually get free check taken from somebody else's paycheck. Okay. And then the top, whatever X percent of taxpayer pays a vast majority of the, or a big proportion of the tax. And they say, well, that's not fair. Okay. Why should the top 1% pay, say, 20% or so of the tax? Or why should the top 10%, say, pay more than half of the tax, and so on? Well, the exact number will differ, but the argument is saying that I want to look at the fairness ratio between the fairness value of the taxation vector versus the pre-tax income distribution vector. Now, both sides of the argument have a point. And if you want to look at the fairness of taxation, you need to look at both sides. So maybe we can plot this versus this as we change the tax rates. Now, the tax rates, there are so many points there, and the tax code, at least in the US, is complicated to say the least. So let's just pick one single point to wiggle, and that is the highest tax brackets tax rate. Okay, and then let's try to varialize that number from, say, 25% to 75%. It actually has gone to much higher than 75%. You cannot go above 100%, of course. But let's say we look at this range, okay, and say, suppose we vary the highest tax bracket smoothly between the low point of 25 and a high point of 75. What would happen to the trade-off curve? The trade-off curve between the New York Times editorial argument and the Wall Street Journal editorial argument, between these two metrics. So we took the 2009 income distribution in public domain data and the 2012 federal income tax rates in public domain data. And here is the kind of trade-off curves that we obtained. On the x-axis is the New York Times editorial argument. Y-axis is the Wall Street Journal editorial arguments. Okay, so this is the fairness for post-tax income versus the fairness of pre-tax. This is the fairness of taxation itself over pre-tax income. And you see that as we vary the highest tax rate from 25 to 75, we go down a slide like this, okay, which is not linear, but if you look at, say, this range, okay, and then you do a linear approximation between these 2 points, you see a very interesting observation. And this illustrates one of the difficult issues behind the taxation debate, and that is the exchange rate between the two axes is about 1. It's not exactly 1, but close enough. That means for every 1% of increase in the income redistribution fairness, there is about a 1% reduction in the taxation burden fairness. And if you look at the scale of the y-axis, you will see that it drops rather quickly. More than 25% of the fairness in taxation revenue contribution is already lost. And yet the x-axis value remains very small. It is very hard to make x-axis big without making y-axis very small. So whether it's a relative trade-off or the absolute scale, we're facing a difficult issue here. And of course, there's much more than just that single trade-off graph using our fairness metric. There's much more to the debate of taxation. For example, within US, there are about 20 different taxes that most of us have to pay. It's not just about the federal income tax. We have also ignored the very important feedback loop. Sometimes raising the tax rate reduces the tax revenue, and that's because human beings are intelligent agents reacting to the taxation rules. So once you put that in the feedback loop, you may see that revenue increases with lower rate. Equally important to the fairness debate is how is the tax dollar spent? The effectiveness, efficiency, and accountability of spending is as important as the side of coin about collecting the taxes. Then there's also a fundamental difference between income derived from merits and income derived from, say, corruption. It often matters a lot whether in a society one's own effort can realize each person's different potential to the fullest. And similarly, there's a fundamental debate between the role of government and the role of self-reliance by individuals. So there's a lot more to taxation fairness debate than just a trade-off curve, but we used it to illustrate in the socioeconomic setup the kind of fairness metric that we can use. So we have seen how to quantify fairness in economic, social, or technological network resource allocation through a set of axioms. And this resembles the kind of axiomatic constructions on voting and bargaining that we saw back in Lecture 6. We didn't have time for this, but in the flipped classroom environment at Princeton, we also will reverse engineer the fairness function parameters such as beta and lambda by asking a sequence of questions to each student. Now, reverse engineering is not news to us either. We have seen that in reverse engineering topologies, in reverse engineering network protocol, and we can also reverse engineer, in this case, the underlying parameters in each person's different fairness function. So fairness highlights the interdisciplinary nature of our study of these 20 questions about social, economic, and technological networks. Now we have reached the end of these 20 questions. It's been a long pursuit, and it only covers the tip of the iceberg. As one once said that it doesn't matter how much that you covered in the course, but how much you have uncovered. And I think we've certainly uncovered a lot. I think I'm going to create another set of slides and another recording coming up that summarize the kind of messages that unifies these 20 questions, the kind of connections that bind these 20 questions together, and the kind of take-home ideas that I hope will stick to your mind for a long time to come, even after you have forgotten the details and the mathematics in these 20 lectures. So until then, I will see you maybe in that lecture 21 of this course on 20 questions.